All right, I'd just like to go over lesson 5, functions and function notation. So the first part of the lesson we want to look at is we want to sort relations into functions and non-functions. And then we're going to look at function notation today as well to solve problems. So one thing I often do is I like to start like a definition of a function. And the definition of a function is basically for each input, for every input, okay, so for every x value, those are our inputs. For each input, okay, whoops, let's not do that in highlighter. For each input, we get one and only one output. That's the definition of a function. So sort of a loose definition, yes, but sort of sometimes a real life example. I say if I am a customer and I go and I try to buy a pumpkin, and I go up to the till and I am charged $5 for that pumpkin. Okay, and then someone else goes and they buy 2 pumpkins and they're maybe charged $10. 5 times 2, or they're charged, $10 for those 2 pumpkins. That's fine. Looks like, for each input we're getting a different output. And then someone else goes up to the till, cash register, and they buy 2 pumpkins and they are charged $8. They're right behind me in line and they're charged $8. Well, that's not a function because here we input 2, right? We input a 2 into the little function machine, into the cash register. Okay, we put in a 2 and we got out either a 10 or an 8. So graphically what that means is for 2 pumpkins, if these are, 1 and 2, and maybe these are going up by 5 and 10 and 15, okay, we got an 8, we got a 2 and an 8, or a 2 and a 10. So then we say, well, we got 2 outputs for 1 input. And then sometimes we do what's called the vertical line test, right? And if I have 2 different outputs for 1 input, right, then I know that that's not a function. So the definition for each input, we should get 1 and only 1 output. Now, if we look at these definitions here, we've got a few. It says, these relations are functions. Okay, there's a relationship here we get a 2 and a 3 and a 4 and a -1. There's no repeating. It would still be a function if we had another, 4 and a -1. Okay, that input of 4 is getting the same output of -1. So that's still a function. Okay, all of these, there's no repeating x's that are giving a different y value. So that's a function. If I do that vertical line test, like I kind of mentioned, no matter where we touch on these graphs, we're going to touch once and only once. So here for the input of 6, here for the input of 6, input x, we've got something around, I don't know, it's hard to see exactly. We'll just say around 4.5, okay? So for each input, I'm only going to get 1 and only 1 output. Same with this ray graph here, okay? For an input of 1, we get a 1. For an input of 4, we get a 2, and so on. Now, those are functions. These are non-functions, okay? For an input here of 12, for an input here of 12, we get an output of 10. And then for an input of 12, we get an output of 14. We can't get a different output for the same input. And if we were to graph that, right, I keep trying to write with my highlighter. If we were to graph that, right, where we've got a 12 here, we've got a 10, a 14, and a 16. A 10, a 14, and a 16. I cannot have 3 outputs for 1 input. Okay, vertical line test touches more than once, not a function. Same with this one. I get a 1 and a 2, a 1 and a 4, not a function. A circle is a relation, not a function. Okay, we get 2 outputs for our single input. Same with this graph here. Right, we can see this one's probably one of the easiest ones to see. Right, for an input of 6, we get 5. And for an input of 6, we get -4, I think. I can't quite see. It's a little small. But anyway, yeah, looks like 6, 5, and 6, -4. So that's not a function. Vertical line test, and we can see for each input we're getting 2 outputs. Okay? Same with this. Here we're putting in a 4 and getting a 1, or we're putting in a 4 and getting a 2, right? These are the x's and these are the y's. Functions, non-functions. So that's sort of a boring, non-glamorous definition of what's a function. Sort of something we just have to understand, a little bit of memorization. And like this one here, here's that vertical line test. Drawing a vertical line, it touches once. There's no place where I can draw on this line that it will touch more than once. Here, we can clearly see that if I draw a vertical line anywhere, that's going to touch more than once, not a function. Okay? So the next one says, determine whether each relation is a function or not a function. Justify your answer. So if we look at this first question here, okay, the x's and the y's, if we look, all of these x values are different and they each have the 1 output. There's no reason for me to think that that is not a function. I have no evidence to suggest otherwise, so I would say yes, that's a function. Okay, let's do that in. Okay, yes, that's a function. And I would say, I guess, if we wanted to justify, right, let's justify, we would say there is 1 output, which is our y value, for each input. Okay, so far we have nothing to say otherwise. But if we look at the next question, here, I've got a 4, and I get a 4 and a 1, and I get a 4 and a -17. That's kind of drawn strangely. But for my input of 4, I've got 2 different outputs. Or for my input of 5, I get -2. For my input of 5, I get -14. Okay, so that's definitely a no. That is not a function. Okay, that's definitely not a function. And the justification for why that is because there is more than 1 output for each input. Okay, and then this third one, is this a function? That's a yes, and the reason that's a yes is because no matter where I draw a line along this, right, I can draw a line anywhere, a vertical line, it will only touch that graph once. Okay, so our justification, okay, vertical line test, only intersects the graph once, anywhere. Okay, there's no way that we can draw a vertical line and it'll touch more than once. So there's sort of some loose definition. Oh, here's a couple more down here. If I draw a vertical line here, look at that, it's going to go through all of those points. Definitely not a function. My input of 3, right, here's a 3, 4, a 3, 3, a 3, 1, right, a 3, -2. That input of 3 is getting more than 1 output, so not a function. That's a broken cash register. That's a no. And then, of course, this one over here is also a no. Okay, and this is also a no. I'll just explain. Okay, vertical line test, right, for each single input, we've got 2 outputs, and 2, 5, 2, 7 for each single input, 2 outputs. Okay, so for all of these, we could say there are more, or there is more than 1 output, more than a single output for each input. Okay, so that's kind of the first part of this lesson. Okay, so the next part is function notation. And that's new for Math 10. Okay, I don't think you would have seen that in grade 9. But function notation, as defined here, says a symbolic notation used for writing a function. The notation f of x is read as just that, f of x or f at x, where y equals f of x. So what does that really mean? Normally, in grade 9, we would say y equals 7x minus 23. Now in grade 10 rather, we'll sometimes write f of x equals 7x minus 23. So what does that really mean? Well, it says a function is like a machine that has an input. Okay, our input is our x's, and our output is our y's. Try inputting a value of x equals -2 into the machine and determine the output. So I'm going to put an input of, I don't know where it's kind of going, I guess it's going right here. We're putting in x equals -2 into the machine, and what's going to come out? Well, if we put x into this machine, okay, that's like saying x equals 2, or it's like saying the value of the function when x is 2, f at 2, which means 7 times 2. What's the value? The value of a function is the y value, okay? So what's the value of the function when x is 2? What is the y when x is 2? So f at 2 means 7 times 2 minus 23. That would be 14 minus 23. And 14 minus 23 would, of course, be -9. So when we're doing that, okay, here's our output, -9. So that's a fancy way of saying, you know, what is the value when x is 2? Now, what's different with function notation? Before, okay, we would say y equals 4x minus 3. Now we're saying f of x equals 4x minus 3. Determine the value of y when x equals 5 is how we would say that. We would sub a 5 in for x into our formula, and we would solve and get 17. In function notation, we say find f of 5. So I sometimes tell students, I say x, right? X has been replaced with 5. So where we see x in the equation, we're going to put a 5, like this down below here. Okay? Now we put a 5, and we still get 17. F of 5 is 17. And all that really is that f of 5 is 17. That's a coordinate, set of coordinates on a graph where if x were 5, if we were to graph this function, f of x is 4x minus 3, or y equals 4x minus 3, we would have a point on the graph would be 5, 17. Okay, determine the value of x. So in Math 9, we would read it like this. Find the value of x when y is -15. We would sub in -15, and we would solve for x. In grade 10, we say determine the value of x when f of x equals -15. Same idea, solve for x. So let's do a couple of examples. Now, sometimes you're given an equation like that up above. Sometimes we're simply given a graph. So if I look at this first graph, find the missing value using the following graph, f of 2. Well, that, if I think of f of x, right, x has been replaced with 2, so we're looking at what is the value of the function when x is 2. I find 2 on the graph, I go up, and the value there is 5, okay? F of 2 equals to 5, which that's just the point, 2 comma 5. F of -3, I find -3, which is right there on my x-axis. This is, of course, x, and this is y. And I go up, 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 up. When x is -3, y is 10. F of 0, here's my 0. When x is 0, y is 1. Now this next one, f of x equals 5, that means the value of the function, which is the y value, is equal to 5. So I'm going to zoom across in the blue here. Well, I can see when my value here is 5, there's my 5. My x could be 2, or x could be -2. right? So here, this point, it's a negative 2, 5 or 2, 5. So here we would say x equals plus 2, x equals negative 2, or if we want to be really fancy, plus or minus 2. Okay, and then the last one, f of x equals to 9. I'm going to draw right across 9. It's a little bit hard to tell here because that 9 is not perfectly, that number isn't quite perfect. It's about, 2.7 or something, or 2.8, maybe 2.9. I'm going to guesstimate 2.9 and 9, and this is negative 2.9 and 9. Okay, so we would say x is plus or minus 2.9. Okay, it can't be 3 because it's negative 310 and positive 310s, right? This is like 310. Anyway, not the best number to choose. Perhaps a little bit tricky just because it's not perfectly on the grid, but that's okay. Hopefully that makes sense. We're finding x or we're finding y. Now this next question here, f of x is negative 1/3 x minus 5. So there's our function. We're asked to find f of 3. That, if I think of f of x, x is replaced with 3. So I'm going to put a 3 in wherever I see an x. So f of 3, negative 1/3 times 3 minus 5, negative 3. So let's just slow it down with the fraction here for a second. Okay, this is 3 over 1. So negative 1/3 times 3 over 1. Remember when we're multiplying fractions, we just multiply straight across, right? We remember that. We don't use it all the time. So let's just not panic too much. Those fractions can be frightening. Negative 1 times 3 is, of course, negative 3, and 3 times 1 is 3, minus 5. I'm just going to rewrite this. We're running out of room here. F of 3 is negative 1. Negative 3 divided by 3 is negative 1, minus 5. So f of 3 is negative 6, right? I take away $1 and I take away $5 out of my wallet. I've taken away $6. I'm spending a lot. I've spent $6, okay? So this means when x is 3, y is negative 6. That's a coordinate, x and f of x, right? When x is 3, the value of the function, the y value is negative 6. The next one, a little bit nonsensical. We're not going to come out with a value here, but we're going to come out with an expression. It's just sort of a review of polynomials. So we're going to replace x with x plus 5. So that's going to be 4 times x plus 5 all squared. Where we saw x here, we're going to put in an x plus 5. And of course, that's a minus 2. And so now how to expand this? This is x plus 5 times x plus 5 minus 2. More than one way to do this. I like to FOIL first, then multiply in the 4. Some of you may know that we don't have to do that. We can do this x squared plus 5x plus 5x plus 25 minus 2. I just FOILed out the x plus 5s. And now this is 4 x squared plus 10x plus 25 minus 2. Combined my like terms. Let's put those like terms together. We get our 10x. And now let's FOIL through, or rather distribute. Not FOIL. FOIL is when there's two sets of terms. Distribute. So we've got our 4x squared plus 40x plus 100 minus 2. And our final answer is going to be 4x squared plus 40x plus 98. So that's sort of math polynomials review. All right, and the last one here says consider these two functions, f of x and g of x. Evaluate f of 0 minus g of 0. Well, f of 0 will be 0 squared plus 5, right? I'm going to replace my x with 0. So f of 0 equals to 5. And g of 0 is equal to 4 minus 0. So g of 0 is 4. And now we want to take f of 0 and subtract g of 0, which is 5 minus 4, which is 1. Right? Our 5, subtract our 4. 5 minus 4 is 1. I know this isn't a try, but maybe I'll give you a minute to try these couple of questions here. Okay, I'll give you a second to try these couple of questions. Yeah, oh, I guess there's some tries coming up, so why don't we finish these ones? I feel like I'm talking way too much, but let's finish these ones. So this one, f of x equals 12, and we know this is a fancy way of saying y equals 5x plus 2. So this is like saying y equals to 12. We're going to plug in that 12. We're going to subtract 2 from both sides. 5x is 10. Divide by 5, x is 2. Okay, so we just found f of 2 equals 12. That's the point 2, 12. And the next one, the last one here for function notation, I guess it says, given f of x is negative 3/4 x plus 5, the point k negative 13 exists on the graph to determine k. So k is a fancy way of saying x, and we know that y, or x and f of x, okay, we know that y or f of x is negative 13. So we're going to plug our negative 13 in for f of x. Negative 3/4 k plus 5. They want us to solve for k. We're really solving for x. And so I'm going to subtract 5 from both sides, just like we know with our algebra. We're going to isolate that x variable, or the unknown variable, the k variable in this sense. Negative 13 minus 5. I spent 13 and I spent 5. I've spent $18. Negative 3, I'm just going to rewrite that, 3 times k, negative 3k over 4. Now this is a proportion. A proportion is a fraction, an equal sign, and a fraction. Okay, that's a proportion, just as a reminder. And the best way to solve or simplify proportion is, of course, to cross multiply. So we've got our negative 18 times 4 and negative 3k times 1. So we get negative 3k is equal to negative 1836.72, and divide both sides by negative 3, and so k is positive 24, right? Those two negatives cancel, and we get 72 divided by 3 is 24. Okay, the last question here before we get... So for this last one, I don't really like the way it got written here, but it says the temperature in degrees Fahrenheit can be determined from a temperature in degrees Celsius using the following equation. So I would rewrite this. I would say F equals the Fahrenheit, okay, Fahrenheit is equal to 1.8 times Celsius plus 32. Now that's the formula. Then it says rewrite the formula using function notation. So F of C, the Fahrenheit, given the Celsius, is 1.8 times Celsius plus 32. And now this says determine F of 25. So when C, F of 25 means C is 25. When it's 25 degrees Celsius, what's the Fahrenheit temperature when it's 25 degrees Celsius? So F of 25 is equal to 1.8 times 25 plus 32. And I'm just going to grab my calculator. 1.8 times 25. Literally just going to type that in there. That's 45 plus 32. And 45 plus 32, that's of course 70. Whoops, why am I writing 3? 77 degrees Fahrenheit. Okay, so we figured out what F of 25 is. Explain what the answer means in the context of the question. Okay, this is not just a point. This is not just 2577, which it could be if you were to draw that the relation, this function on a graph. But this means when it is 25 degrees Celsius, it is 77 degrees Fahrenheit. Okay, that's the conversion. All right, and then determine C so that F at C is 100. Well, what is the Fahrenheit? Okay, sorry, let me rephrase that. What is Celsius, right? What is Celsius when the Fahrenheit is 100? Okay, so f of c, 100 is equal to 1.8 c plus 32. We're going to subtract 32. And here we have 100 minus 32, which is, of course, 68, is 1.8 c. Divide both sides by 1.8. And 68 divided by 1.8 is, of course, 37.7. It doesn't say what to round to. We'll round to the nearest, I don't know, nearest tenth. Okay, 37.77 repeating, so the C is 37.8 degrees Celsius. So explain what the answer means within the context of the question. Okay, 100 degrees Fahrenheit converts to 37.8 degrees Celsius. Okay, that's the conversion. All right, now I'll pause the video, and you can pause the video and you can try these tries, see how you can do. Okay, I've filled these in. I won't go through them, but you can go ahead and check your own answers. You can pause if you need to do a double check. And you can see the answers below, but if you need a little more clarification, the answers are here on this page, keyed up. Okay, good luck. If you have any questions or concerns, I'll just scroll down there and pause there. Hopefully you can read that. Please do not hesitate to contact me or your current math teacher. Good luck. Take care.